Start the pumps right now! Move or we sink!
On the evening of July 9, 1958, 3 small fishing boats sat anchored in Lituya Bay, a remote fjord on the southeastern coast of Alaska. The water was glassy. The air was still. It was the kind of night that made the bay's brutal reputation feel like folklore. Aboard the Edry, Howard Ulrich had turned in for the night with his 7-year-old son. Nearby, Bill and Vivian Swanson were settled aboard the Badger. Farther out, near the bay's narrow mouth, Orville and Mickey Wagner rested aboard the Sunwolf. None of them knew that deep beneath their hulls, a fault line had been quietly building toward failure for years, and that within the hour, physics was about to do something to that bay it had done only a handful of times in the last century. At 10:15 p.m., it let go. According to the Alaska Earthquake Center, the Fairweather fault ruptured along roughly 125 miles of its length, from Cross Sound north to Icy Bay, in an earthquake strong enough to be felt from Seattle to Whitehorse. On the boats, gear crashed to the deck and hulls bucked against their anchor chains. It felt for a moment like the worst of it. It wasn't. High above the northeast corner of the bay, on a slope that had been quietly undercut by a retreating glacier for years, a mass of fractured rock finally broke free. Geologist Don Miller, who surveyed the site within days, estimated that roughly 30 million cubic meters of stone, on the order of 90 million tons, peeled off the mountainside and dropped more than 900 meters straight down into Gilbert Inlet, the narrow arm of water at the bay's head. What happened in the next few seconds would be witnessed, in different ways, by all 6 people on those 3 boats. Ulrich watched a wall of water rise at the head of the bay and come straight for him. He had a jammed anchor, a sleeping child, and by his own account, only a few minutes before it arrived. This is the story of what that wave actually was, why this particular bay was built to produce it, how scientists spent 50 years proving what caused it, and what happened to the 6 people anchored there that night, plus the geologist who had been trying to solve this bay's mystery for 6 years already, and got his answer delivered in the most violent way imaginable, from less than 50 miles away. If you've never heard of a wave taller than a skyscraper, stick around. By the end of this, you'll know exactly how it happened, minute by minute, and why it could still happen again. And if stories like this are your thing, subscribe to Keel and Current, because this is only the beginning of what the Earth has done to the people standing on it. Lituya Bay sits on a lonely stretch of the Gulf of Alaska coast, about 100 miles northwest of Juneau, near what is now Glacier Bay National Park. Seen from above, the bay forms a rough T, a 7-mile-long trunk running from a narrow, treacherous entrance at the sea up to a head fed by glaciers, with a short arm, Gilbert Inlet, branching off at the top. Nearly vertical mountains wall in the water on both sides, some rising thousands of feet within a mile or 2 of the shoreline. It is one of the only sheltered anchorages along a long, exposed stretch of coast, which is exactly why fishing boats used it. It is also, geologically, one of the most dangerous pieces of shoreline in North America. The Fairweather Fault runs directly beneath Gilbert and Crillon Inlets, the 2 arms that form the top of the bay's T-shape. So this isn't a place where earthquakes arrive from somewhere else. The fault is part of the bay's geography. The bay had a body count long before 1958. Cenotaph Island, the wooded mound at the bay's center, is named for a French maritime expedition that came to grief there in the late 1700s, when a group of sailors drowned attempting to navigate the bay's violent tidal bore at its mouth. A hazard that has nothing to do with landslides and everything to do with the bay's narrow, current-choked entrance. The name stuck as a monument to how unforgiving this water could be even without a mega wave involved. The Tlingit people, who lived along this coast for generations before European contact, carried oral traditions warning of the bay specifically, stories of a destructive presence in the water capable of rising up and wrecking canoes. For most of the 20th century, that warning remained folklore layered on folklore, a beautiful, sheltered anchorage that occasionally and mysteriously tried to kill everyone inside it. Adding to the danger, the bay itself is deceptively deep for its width. Soundings show a maximum depth of around 720 feet, even though the entrance channel is barely 33 feet deep. A mismatch that matters enormously once you understand what eventually happens when a large mass falls into water that deep with nowhere lateral to spread. The physical evidence behind the bay's reputation was written directly into the surrounding hillsides, visible to anyone who knew how to read it. In the early 1950s, one geologist started reading it very closely, and what he found would turn out to be the key to understanding exactly what this bay was capable of doing to anything anchored inside it. In 1952, USGS geologist Don Miller was working a petroleum survey around the Gulf of Alaska when he stopped at Lituya Bay and noticed something odd. The forest ringing the bay wasn't uniform. Along the slopes, mature old-growth trees gave way abruptly to a much younger band of grasses and saplings, in a sharp, almost surgical line running high above the current water line. Below the line, young growth. Above it, forest that looked centuries old. Miller recognized what he was looking at. A trimline, the geological signature of a wave that had once scoured that slope bare, after which the forest had slowly begun regrowing from the high water mark downward. Digging into the bay's history, he learned that a similar, locally famous event had struck in 1936, one that older residents could still describe firsthand. Other researchers had floated the idea that a subglacial lake bursting its ice dam might explain it. But Miller found the bay's topography didn't support that theory unless there was a hidden chamber under the ice nobody had ever located. By comparing trimlines at different elevations around the bay, Miller eventually concluded there had been at least 4, and by some later counts 5, giant wave events over the preceding century, with run-ups as high as 490 feet on some slopes, a rough recurrence, he estimated, of roughly every 30 to 40 years. What he lacked for years was a confirmed mechanism. Shaking alone didn't obviously explain waves that size in a bay shaped like this one. Miller kept a rough base camp on Cenotaph Island through the 1950s to keep studying the problem. On the night of July 9, 1958, he happened to be nearby, aboard a USGS survey barge over in Glacier Bay, when the earthquake hit. He felt the barge heave and watched rock falls tumbling off nearby cliffs in real time. By morning, word reached him that something catastrophic had happened at the exact bay he'd been quietly obsessing over for 6 years. He chartered a float plane immediately. What he found when he got there didn't just answer his question. It answered it in the most extreme, unambiguous way nature had ever demonstrated a mechanism to a scientist studying it. Rafts of shattered logs were fanning out across the open ocean 5 miles from the bay's mouth. The bay's surface was so choked with tree trunks and ice blocks that his pilot couldn't land. And ringing the shoreline was a stark new trimline, fresher and far higher than anything he had measured before. The Fairweather Fault is one of the most active strike-slip faults in North America, part of the boundary zone where the Pacific Plate grinds northwestward against the North American Plate. Modern seismological analysis, including the USGS-linked catalog record for the event, puts the earthquake at a moment magnitude of 7.8, though some contemporary estimates from 1960 ran as high as 8.3. The uncertainty is a reminder of how much seismology has advanced since instruments of that era tried to measure a rupture this large. Either way, it was the strongest earthquake to hit the region in over 50 years, since a magnitude 8.2 quake near Cape Yakataga in 1899. On July 9, 1958, roughly 125 miles of the Fairweather Fault ruptured in a single event, with ground displacement along parts of the fault reaching several meters. The shaking caused real damage well beyond the bay itself. In Yakutat, about 100 miles up the coast, it wrecked bridges, docks, and a water tower, and offshore underwater landslides severed communication cables. But the earthquake was not on its own what produced the wave. It was the detonator, not the explosion. That distinction turned out to be scientifically crucial, and it took decades of modeling to nail down exactly how the two were connected. Miller himself, surveying the bay in the days afterward, initially wondered whether the ground motion of the earthquake alone might have sloshed the bay violently, a phenomenon known as a seiche. But once he saw the scale of the fresh rockslide scar at the head of Gilbert Inlet, he became convinced the landslide itself, triggered by the shaking, was the true cause. That hypothesis held up under decades of scrutiny. Researchers including Herman Fritz's team at Georgia Tech, who built a 1/675 scale physical model of Gilbert Inlet in a Swiss laboratory in the early 2000s, and later teams using computational fluid dynamics software to simulate the event in 3 dimensions, consistently found that a rockslide impact, not fault displacement or shaking alone, was necessary to reproduce the observed 524-meter run-up. An earlier, simpler modeling attempt from the late 1990s that didn't account for the landslide's full impact energy failed to come anywhere close to that height, which helped confirm the landslide really was doing almost all the work. The fault started it, the mountain finished it, and it took the scientific community roughly 50 years after the event to fully agree on the details of how, precisely, that handoff happened. At the head of Lituya Bay, Gilbert Inlet branches off to the north, hemmed in by a slope tilted at roughly 40 degrees, the kind of angle that looks stable for centuries, and then, all at once, isn't. That slope had spent years being undercut by the glacier at its base, its rock progressively fractured and loosened by the ice's slow retreat. When the Fairweather fault ruptured, the shaking did to that slope what it had apparently done at least 4 times before over the preceding century. It broke the mountainside's grip on itself. By Don Miller's estimate, roughly 30 million cubic meters of rock, on the order of 90 million tons, essentially a chunk of mountain the size of a small city block stacked hundreds of feet high, sheared away, and fell more than 900 meters, nearly a kilometer, straight down the slope into the water of Gilbert Inlet below. Later modeling by geophysicist Robert Weiss and colleagues, built to reproduce the observed wave height, estimated the rock mass hit the water at an impact velocity of around 110 meters per second, roughly 245 miles per hour. That is a mountain's worth of stone slamming into a narrow, enclosed body of water at just under the cruising speed of a jet airliner. Witnesses in Yakutat, nearly 50 miles away, reported hearing the impact. The impact did 2 distinct things, which is part of why the event is so scientifically unusual. It punched a large air cavity into the water, a temporary void created by the rock mass, around which a highly nonlinear soliton-like wave formed, and immediately began surging up the slope directly opposite the impact point. Separately, it generated a second, lower wave that began racing down the length of the bay toward the open ocean, more like a conventional, if still enormous, tsunami. The first wave is the one that made history. The second wave is the one that nearly killed 6 people in boats more than 5 miles away.
Hold on tight.
Understanding why those 2 waves behaved so differently from each other, and from anything a normal earthquake tsunami produces, required scientists to rethink what a wave could even mean in a setting this confined. Peer-reviewed numerical modeling published in 2019 by a Spanish research team put numbers on just how fast this all happened. The wave reached its maximum amplitude of roughly 272 meters about 8 seconds after impact, and slammed into the spur ridge opposite the slide, reaching its full 524-meter run-up at around the 39-second mark. From the moment the mountain hit the water to the moment it had already carved its record into the mountainside across the inlet, well under a minute had passed. There was no warning beyond the earthquake itself, and no time for anyone in the bay to do anything but react to what they could already see and hear. Most tsunamis are earthquake tsunamis. The seafloor itself lurches vertically across a broad area, displacing a huge volume of ocean water all at once. That displacement spreads outward across an entire ocean basin, and by the time it reaches a coastline, the energy has dispersed enough that even a devastating tsunami is usually a matter of a few meters of run-up, occasionally more in unlucky coastal geometries, but rarely anything close to what happened at Lituya Bay. Lituya Bay was generated by an entirely different mechanism, one that geologists now classify separately as a landslide-generated impulse wave, or, when extreme enough, a megatsunami. Instead of the seafloor moving, a solid mass, in this case a mountainside of rock, fell into the water from above and displaced it directly, all at once, in an enclosed space with nowhere for the energy to spread. The comparison researchers reach for is a rock dropped into a bathtub. In open water, a falling mass displaces water in every direction, and the resulting wave is modest. In a narrow, steep-walled inlet like Gilbert Inlet, the water has almost nowhere to go but straight up the opposing slope. Energy that would normally disperse across miles of open ocean instead concentrates into a violent vertical surge against one specific stretch of mountainside, directly across from the impact point.
But still monstrous.
This is why the two numbers tied to the event are so different from each other. The 524-meter figure is a run-up height, essentially how far up the opposite mountainside the initial splash climbed before gravity pulled it back, not the height of a wave crest moving through open water. The separate wave that then traveled the length of the bay toward the three fishing boats was far lower and dropped fast as it spread out. Modeling shows it still carried a wave amplitude of around 200 meters near Mudslide Creek on the south shore, roughly 30 meters by the time it reached Cenotaph Island, and closer to 15 to 20 meters by the time it neared the bay's entrance, still enormous by any ordinary standard, but nothing like the run-up figure that made headlines. Eyewitness timing later suggested the wave crossed the bay at somewhere between 97 and 130 miles per hour. Physical model experiments run at engineering labs in the 2000s, later validated against three-dimensional computer simulations from teams in Germany and Spain, confirmed this mechanism in detail. The impact velocity, the slide's shape, and the geometry of the inlet all had to be modeled together to reproduce what actually happened. It remains one of the best documented landslide tsunami events in the scientific literature, precisely because nature left such precise physical evidence of exactly how high the water went. Scientists didn't have to take anyone's word for how tall the wave was. The mountainside recorded it directly, and the record was unambiguous. Where the wave hit its maximum run-up, on a ridge spur almost directly across from the slide, it stripped away everything. Full-grown trees, root systems, and the soil itself, scouring the slope down to bare bedrock. Above a certain elevation, the forest stood completely untouched. Below that line, there was nothing left but raw rock, in places for hundreds of meters up the incline.
Lituya Bay.
That boundary, the trimline, could be measured with a surveyor's precision. And when Don Miller and later researchers did the math, the maximum point came out to 524 meters above sea level, about 1,720 feet. For scale, that is taller than the Eiffel Tower by roughly 200 meters, and taller than the Empire State Building, including its antenna. It remains, decades later, the highest wave run-up ever documented on Earth. Around the rest of the bay, the destruction was almost as staggering, if less extreme at its peak. Over 1,000 feet of ice sheared off the face of the Lituya Glacier at the head of the bay. The overall trimline of forest destruction extended for miles along the shoreline, in places reaching several hundred feet up the slopes, consistent with, but generally lower than, the maximum point directly opposite the slide. A lighthouse that had stood at Harbor Point near the bay's entrance was simply gone. Trees 4 feet in diameter had been sheared off and stripped of bark by the passing water and debris. This physical record is what eventually allowed skeptical scientists to accept a number that initially sounded almost too extreme to believe. When early reports described a wave that had climbed over 1,700 feet up a mountainside, it was easy to suspect exaggeration or simple measurement error. But a stripped, bare mountainside doesn't need a witness. Miller's aerial photographs of the scoured slope, taken within days of the event, became some of the most cited images in the history of tsunami science, visual proof of a number that redefined what scientists believed was physically possible for a wave to do to solid rock. Those same photographs are still referenced in tsunami hazard research today, more than 60 years later, because so few landslide-generated waves have ever been documented with this much physical precision immediately after the fact, before rain, regrowth, and erosion could soften the evidence. Of the 3 boats anchored in Lituya Bay that night, Howard Ulrich's had the best vantage point on the disaster, because he watched almost the entire thing unfold from the moment the mountain fell. Ulrich later told Don Miller he saw the wave rise at the head of the bay, an enormous, rising wall of water, and heard a roar loud enough to leave no doubt about what was coming. He secured his sleeping son's life jacket, tried to start the engine, and went for the anchor. It wouldn't budge. The chain had jammed. A boat still tethered to the seafloor in front of an oncoming wall of water is, in essentially every scenario, a boat that capsizes or is driven under. Ulrich had only moments to make a decision, and he made the right one. Rather than continuing to fight the anchor, he gave the engine full power and let the wave itself do the rest. The force of the water tore the anchor chain free on its own, snapping it rather than requiring him to free it by hand. What followed was less a collision than a ride. Ulrich's boat, the Edry, was lifted up the advancing face of the wave, carried up and over its crest, and set back down on the far side as the wave continued rolling past toward the bay's entrance. He kept the boat under control through the whole sequence. When the water settled, both he and his son were still alive, still aboard and still afloat. A genuinely remarkable outcome given that they had just ridden out, at close range, what remains the largest wave ever measured on the planet. Ulrich's account, given to Miller in the investigation that followed, became one of the primary eyewitness sources for reconstructing exactly how the wave behaved as it moved down the bay. How fast it was traveling, how it interacted with the boats caught in its path, and how the initial run-up wave near Gilbert Inlet related to the lower, still massive traveling wave that raced the rest of the length of the bay toward open water. Without his testimony, much of what scientists later modeled about the wave's behavior in the outer bay would have been guesswork. It's worth pausing on how narrow that outcome was. A few seconds delay reaching the throttle, or an anchor chain that held instead of snapping, and the story of the Edry almost certainly ends differently. Ulrich himself would later describe the decision as instinct more than calculation. There simply wasn't time for anything else. The Swansons, aboard the Badger, experienced something even harder to reconcile with ordinary physics. Their boat was picked up by the surge, carried backward, stern first, and swept clean over a spit of land at the bay's entrance that normally sat well above the waterline. Vivian Swanson later described looking down during the ride and seeing treetops beneath the hull, which gives some sense of how much water was moving through a space that, on any ordinary day, was simply solid ground. The Badger was dropped into the open ocean on the far side of the spit, damaged and taking on water. The Swansons abandoned it for a small dinghy and were picked up by rescuers a few hours later, a second near-impossible survival story from the same few minutes. Modeling of the wave's progress suggests it took roughly 2 minutes to reach Cenotaph Island in the middle of the bay, and nearly 6 minutes to reach La Chaussee spit at the entrance where the Badger and Sunmore were anchored, which meant the Swansons and Wagners had slightly more warning than Ulrich did at the head of the bay.
We made it through.
But a wave that size loses very little of its danger, even after miles of travel. The Sunmore, anchored closer to the bay's mouth, did not get the same outcome. Orville and Mickey Wagner appear to have tried to run for the entrance and open water once they realized what was coming, but the wave caught the boat near the mouth of the bay and swept it away entirely. Neither the Wagners nor significant wreckage of their boat were recovered afterward. Of the 6 people anchored in Lituya Bay on July 9, 1958, 4 survived: Howard Ulrich, his son, and the Swansons. 2 did not: Orville and Mickey Wagner. It's worth separating this from a number that circulates in some accounts of the broader earthquake: 5 total deaths that night across the whole region. That figure includes 3 more people killed roughly 100 miles up the coast, when the earthquake caused part of Kontak Island, near Yakutat, to subside into the water beneath a couple out picking berries with friends. Those deaths were a direct result of the same earthquake, but they had nothing to do with the wave in Lituya Bay itself. Inside the bay, the toll was 2. Given that this remains the tallest wave ever documented striking a populated body of water, a death toll of 2 is a genuinely striking outcome. A reflection partly of luck, partly of the specific paths the 2 surviving boats happened to take relative to the wave's geometry, and partly of quick, correct decisions made with almost no margin for error at all. The wreck of the Sunmore was never located, and no formal account of the Wagner's final minutes exists beyond the fact that other boats saw them attempt to reach open water. That gap in the record is itself part of why the two survivor accounts, from the Edry and the Badger, carry so much weight in every scientific reconstruction of the event that followed. Lituya Bay's 1958 wave is not an isolated curiosity. It's the reference case for an entire hazard category that scientists now take seriously well beyond one Alaskan fjord. The landslide-generated Megatsunami, produced not by the seafloor shifting, but by a mass of rock, ice, or debris falling into confined, deep water. The ingredients aren't rare in the way the outcome is. They're simply a steep, unstable slope, deep water directly below it, and a trigger, usually an earthquake, sometimes just gravity and time acting on rock that glacial retreat has left unsupported. That combination exists in fjords across Norway and Greenland, in glacially carved valleys throughout Alaska and Chile, around volcanic island flanks slowly sliding into the sea, and even in reservoirs behind large dams. Italy's 1963 Vajont Dam disaster, which killed nearly 2,000 people, was driven by the same basic mechanism on a smaller physical scale, but a far larger human one. Since 1958, researchers have documented smaller landslide-generated waves in similar terrain elsewhere, including events in Alaska's Ton Fjord in 2015 and in Karat Fjord, Greenland, in 2017, both tied at least partly to slope failures following glacial retreat. The Lituya Bay event itself appears to be part of a longer, recurring pattern rather than a one-off. Don Miller's trimline surveys suggest the bay produced comparably large waves roughly every 30 to 40 years going back over a century, with 1958 simply the largest and best documented of the series. In 2016, researchers noted an entire mountainside failed onto the nearby Lamplug Glacier, a reminder that the surrounding terrain is still actively shedding rock. That recurrence pattern and the underlying mechanism is exactly why Lituya Bay has become one of the most studied tsunami events in the world, despite its remote, sparsely visited location. Decades of physical scale model experiments and increasingly sophisticated three-dimensional simulations have used the 1958 event as their benchmark case. Precisely because it is rare to have a landslide tsunami, this extreme paired with such precise physical evidence. A mountainside stripped bare to near surveying precision of exactly how high the water went. The bay is still there, still steep, still glaciated, and still sitting directly on an active fault. Researchers who study the region have noted that terrain destabilized by the 1958 event, combined with ongoing glacial retreat exposing more unsupported rock, means the underlying hazard hasn't gone away. It's simply waiting, the way it waited quietly for the century before 1958 for the next trigger. That's the story of the tallest wave ever measured, and the 6 people who found out in under a minute exactly what this bay was capable of. If you want more stories like this, moments when the Earth reminded people who's actually in charge, subscribe. Drop a comment with what you'd have done in Ulrich's place with a jammed anchor and 3 minutes on the clock. And check out the next video, where we go inside another disaster that rewrote what scientists thought was possible.